Hello people and welcome to my channel. My name is Milos and I'm a creator of original maps which I regularly post on Instagram and Twitter. I'm back with another data visualization and GIS tutorial, and this time I'm going to show you how you can easily perform zonal statistics with R. Zonal statistics is one of the most important spatial techniques used for determining the values of a certain zone of interest, and it is widely used in environmental scientists, urban planning, resource management, agriculture and crop management, as well as public healthcare. In this specific tutorial, I will show you how you can access satellite imagery from MODIS, and then I will show you how you can load a global land cover dataset from MODIS using a package in R, which will serve as a client for communicating with the MODIS API. And then using zonal statistics with R, we will actually calculate what is the percentage of area for every region in Ukraine that has a certain land cover class. I will also show you how you can perform this analysis on a single as well as multiple classes of land cover. Finally, I will also show you how you can create several powerful data visualizations. Without any further ado, let's roll. All right, we are back in R, and the first thing we will do here is set our working directory. This is going to be my working directory, so I created a separate folder, which is called Ukraine Land Cover, for an obvious fact, because we will be working on the land covered data set and especially on the zonal statistics of this data set for the Ukrainian regions. And after we set the working directory, let's create an object where we will store the path to the main directory, because later on we'll be using this to save some of the objects as we load them into R. Then the next step is to install three necessary packages, three critical packages for this R session from their respective sources. So basically from the GitHub repos where they are. For that purpose, you need to install package remotes if you already don't have that one, because next thing we will use remotes and it's install GitHub option to install these packages from their respective GitHub repos in the following way. So we use remotes, install GitHub, and then we specify name of the repo / name of the folder or the package that we want to install. The first one comes from our Open Science, and that is the package which is actually a client that communicates with the MODIS API, and it can get you any of the datasets from MODIS API in the raster or dataframe format as you wish. So this one is called MODIStsp, and it's based in our Open Science repo. Then the next package, we will also use this remotes install, and this one is actually used to load any country shapefiles as well as substate shapefiles for any country in the world. This one comes from a personal repo, DicOA, and it's called R GeoBoundaries. Basically, this is an R client for GeoBoundaries library that will help us load the shapefile of Ukrainian regions directly into R. So R GeoBoundaries. And then the third package that we want to install from the source is used for the zonal statistics itself. It allows for some of the standard zonal statistics functions, such as, for example, minimum, maximum, and average values, but it also allows you to customize your function based on the number of classes that you have. And this is ideal for us because for the land covered data set that we'll be using, we'll have anything between 1 and 15 classes of land cover. So this one is called, it has a bit of a weird name, extract R. In essence, it's used to do zonal statistics. This one comes from a repo, eSciences. So shout out to all of these, three repos and creators of these packages. Pretty useful for our purposes here. So then we simply run all of these codes, and as you install each of these packages from their respective sources, you will be prompted to choose one of, I would say, 20 or even more options. So it's basically whether you want to install also some of the dependencies for these packages. I would go for option 3, which is do not install dependencies, which you may already have. So this is it. We just run all this, and in the next step, we then load the packages. Now you hopefully managed to install those 3 critical libraries that we'll be using throughout this tutorial. So our next step is to define the set of libraries that we want to load into this R session. So libraries we need, and we're going to proceed as follows. We're going to create an object libs, which is actually going to be a list of strings where each string represents the name of the package that we want to load. Of course, the 3 of them we've already covered in the previous section where we installed them. And one of them is MODIStsp, which is a client's library for communicating with the MODIS API and getting into our the raster files of satellite imagery that we need. The second one, which we also previously installed from the GitHub repo, is RGeoBoundaries, which is another client package for communicating with GeoBoundaries and getting the shapefile, in our case, of Ukraine and specifically Ukrainian regions into R. There is another library which is very useful for data wrangling and data visualization with R, and actually it's an umbrella package which is called Tidyverse. We're specifically going to use 3 libraries from Tidyverse: dplyr, tidyr, both of them for data wrangling in different spheres, and finally ggplots2 for creating beautiful visualizations. In order for us to work, load, and save these shapefiles from our GeoBoundaries, we need the asset package. And then to work with the raster files that we get from MODIStsp, we're going to use terra library. And then one of the packages that we previously also installed and that we're going to use here for zonal statistics, it's called exact extract R. So exact extract R. And then finally, at some point, we will also want to scrape part of the MODIS website and also get its codebook directly into R so that we can actually label the classes that we got from the MODIS API. And this one is package HTTR. All right. Now, it can happen that some of these libraries you don't have installed in R. So we need to make sure that we install missing libraries. Now this is going to be straightforward because we already here defined libs. So in order for us to see if these libraries are installed, we're going to create an object called install libs. And then we're going to check within libs if these are truly installed. So and then we're going to check row names of installed packages. All right. So this is we're gonna check. Now, if these are not inside, so if any of installed libs are actually false, so if they're not there, then we open curly brackets, and then within that we tell R install.packages where installed libs are not present inside of libs. All right, like that. And now once we do that, we simply just need to load libraries. And to load libraries, we need to apply actually to the list of libs. We need to apply function library from R and also character dot only equals true. So that's about it. And now if you actually run this code, you will be able to get everything sorted out. So those libraries that are not installed, they're going to be installed, and then everything is going to be loaded into R. In order to download the Ukraine data specifically using MODIStsp package, we first of all need to fetch the substate boundaries of Ukraine, and then we need to save that shapefile to our local drive, and then provide it to MODIStsp so that it can download the tiles we need and then crop them using Ukrainian national boundaries. So as a first step, we'll be using RGO boundaries, and specifically its function, which is called, so it has several ones based on the administrative level that you need. So it can go from 0, which is basically just national boundaries, then it can go to lower and lower levels until it reaches the lowest level, which is administrative level 5. Of course, for every country, these levels mean a different thing, but this is more or less standardized. These are more or less standardized levels, at least when it goes from 0 to 2. So in our case, we're not going to go that lower. We're going to go for the first level. So that's why we'll be using the function gb underscore adm1, which will actually help us then get the region boundaries of Ukraine. And then the only argument you need to here to provide is the ISO 3 code of the country you need. For Ukraine, that's UKR. For other countries, it's going to be something else. And then we're just going to name this object Ukraine poly. We can also say that, it's a level, 1, but because in this case, we are just going to use this regional boundaries of Ukraine, this is going to suffice. Now, if I want to show you whether this is exactly what we got, we can also plot this. The good thing about RGO boundaries package is that this will be in the SF format, so we don't need to do anything else about it. What we can just do is I can just show you here the plotting this shapefile that we got. So Ukraine poly, and then we can simply run this. And once we run, then we can check whether we have the regions. So here they are, 27 regions of Ukraine. And if we also inspect this file, you will also notice that there are some additional fields. But for us, the most important thing is that we got the shapefile we wanted. So now the next step is to save this shapefile on the local drive so we can pass it to MODIStsp. We first need to create a file path to which we want to save this. And we can name this file path. And for this purpose, we can actually use that main file that we created at the beginning and simply pass then to it the name of the shapefile that we want to create. So we're going to use paste null option here, and then we're going to create this slash to actually distinguish between the main pathway and the name of the object. And for the name of the object, we can call it Ukraine underscore level 1, and most importantly, it needs to be format shapefile, so .shp. Once we created this file path, we can finally write this SF object to our local drive, and for that we use SF package and st underscore write. Here we first need to specify the name of the object, so it's called Ukraine poly, and then we need to specify the path to the file, which we just created, and it's called file path. Once you run these both things, what will happen next is the pathway will be created, and then we will write this SF package to the path. Next thing, we will just run this, and then after that, we can actually move on to loading the data using MODIStsp. Before we jump straight into using MODIS data, it's really in order to understand what is actually the data that we're going to download. So here I am on the MODIS website. So it's modis.gsfc.nasa.gov, and then /data/dataprod. This is the page where we have data products, which are based on the MODIS data, and that you can use to study different types of global change. So there's a variety of possible data sets here, which span different disciplines, from environment to oceanography, biology, atmosphere, many different products here. But the one that is very, very important for us in this current tutorial is the land cover products. So MODIS land cover products. When you click on this one, it will lead you to actually the description of this specific product and some details, about how actually this was created. Basically, it was MODIS, Terra plus Aqua combined data, and then creating actually 17 classes, which are defined by this IGBP. So this is the place where you can also see, some product information in sense, who is the principal investigator, what is the validation stage, and some other things. But for us, the most important one is these different layers that we can download. So the first thing that is quite important here that we should copy, basically, is this name. So land cover type yearly L3 global 500 meters. This is the data set that we're going to use. And the second thing that is very important is this code, because this code is going to allow us to load this into R. So to communicate with the API and then load this into R. So if we click on this first code, MCD12Q1, another window will open. And then it informs us here that this data is currently updated to version 6. Do not worry, because this version is also, so version 6.1 is supported by the MODIStsp library in R. So we are up to date when it comes to that. So we are now on this page for the specific version, and it offers some more information about the version itself. But for us, the most important thing is this option layers, because here, once we load this into R, we will be offered the possibility to use one of these layers. So for us, the most important one is actually this first one, because this is basically the classification. It's going to offer us 17 possible values. And it's going to be classification based on this International Geosphere Biosphere Program, or IGBP classification. Now, once we actually choose this layer, we will still have this unknown information about these classes. So 1 to 17, they're not really going to be specified in that raster that we will load into R. So what we need to do to understand what these actually number mean, we need to go up to this page. And then we need to click on documentation. And within documentation, we choose the third link, which is called file specification. This opens up a new page, which is host to a codebook for this specific data set. So over here, we can see how variables are defined, what I actually mean, what are the codes for those variables. So if we scroll down, we will actually notice classes. So it starts with class 0, which is basically water, so it's not really land. But then you have here the codes for 1 to 16. So, for example, 1 is evergreen needleaf forest, and the second one is also forest, and the third and the fourth one, as well as the fifth one. So there are also other options for us. What is really interesting is, for example, croplands. So we would like to then use number 12 specifically for croplands, but you can also use zonal statistic later on, as I will show you, for any other classes, or you can use zonal statistics for all the classes here. So that's also possible. But for now, what is really important is that you actually visit this page and you see this codebook and understand what are the actual codes in the data that we are going to download. While we are still on this page, we need to make one more critical step in order to be able to access any MODIS data, including this one. And this one is about registering with the Earthdata website which actually hosts this dataset, but also other datasets. The way you do that is you click on the login option here in the upper right corner of the screen, and then select Earthdata login option. This will take you to a new screen, which will offer you the possibility to register. So you click here on register, which is for free. You just need to leave some of the information here. One of them is you need to register under a certain username and password, which need to fulfill some of these conditions. And then if you move downwards, you will also see some other things, your first, last name, as well as email, country, and affiliation if applicable. And finally, you need to also agreements, also accept some of the agreements here, and also complete, for example, this CAPTCHA, and then you can finally register at the Earthdata, after which you will get a confirmation email, and you just click on that email, confirm your newly created accounts, and then you can log in here. For the purposes of our tutorial, you would need to copy your username and password because we will be using it in the MODIStsp to communicate with the MODIS API and then download the data specifically using your credentials. All right, we are back in R, but before we dive into coding, I would like you to get familiar with the MODIStsp package and its main functions. So the function from this package that we will use to communicate with the MODIS API and load the data we need, it's also called MODIStsp, so you cannot miss it. Now, it has a bunch of functions here, so we are not going to use all of them. They're not necessary, but some of them, it's really necessary for us to understand because we will be writing that code and it will help us communicate effectively with the MODIS API and get the data we need. One of the functions or one of the arguments within this function is called GUI. This is basically if you want to open general user interface after running this function, which would then help you to manually select the parameters that you want to download. We won't be using this argument in R, so we're going to set it to false because we don't want it to do it manually. We want to write a code that will then execute the query and download the data for us. Other things that you can also set here is, for example, out folder, which is going to be the main output folder that we will use to download the data. So the way this works is once we send the query to the API will return to us the data, but then this data will be downloaded, so it's not going to be kept in our memory. There are also other things that we can specify here, some of them more, some of them less important. So, for example, one of them, which is very, very important, is, as I said before, your user name and your password. So this is where you will be specifying as characters. So as strings, you will be providing this information here. There are also other options that you can specify. One of them that we will also use is, for example, start and end dates. Now, this global land cover data set, it's recording on annual basis. So we are not going to be using here any other level than annual. But to fetch the annual level, you still need to specify start and end dates. The way you do that is the start date will be 1st of January and the end date will be 31st of December that same year. This is how we do it. Then there are different options for downloading your file. And this one is specified by the argument spat_math. So this one can mean several things. Like this is the way that the file will be loaded or returned back to you. So it can be a tile. If you know the specific coordinates that you then you do that. But in terms of the countries, countries are big, so they require more tiles. You can also use pbox, which is a shorthand for bounding box, if you want a certain area to download. And then finally, you can use a file which we are going to use. So we'll be using that file that we, shapefile that we just saved to our local drive. This is what we're going to be using. Then after this one, after you specify here that you want to use file for cropping, then you need to specify the path to your shapefile. And this is argument called sp file that we are going to use. There are some other things that you can specify, because this package is used for also resampling or reprocessing the data from MODIS. You can also specify that. We're not going to go into that. You can even specify the time series formats. You can also specify the format of your file. So we're going to go for the TIFF. And there's so many other things, but this in a nutshell is what we're going to use. So the next step is to finally plug in the information we need into that code, run it, and then finally download the global land cover raster file. Now that we better understood a MODIStsp package and its main arguments, there are still two things that we need to fetch before proceeding forth. So one of them is, of course, what is the name of the product that we want to download, because that's one of the arguments we need to pass to MODIStsp. And the other one, what is the name of the layer? So luckily for us, this MODIStsp package allows us to, for every product, we're using its code, get these necessary info. So let's use MODIStsp, and then MODIStsp prod layers. Get prod layers, this is the one. So here we need to pass that code that we previously copied, if you remember, from that table where we had those three products. So for us, it was MCD 12 Q1. All right, and now I'm just gonna increase this terminal so I can show you what is the output once you run this. So here it is. We here get the product name. This is what we will need to pass to the MODIStsp function of the same package name. So please just copy this one. So this is going to be the product name. And then for the layer name, we'll be using this LC1, if you remember, also from the website. So now it's stored here, so it's easy to understand what's going on. Okay, so I just wanted to show you these two things. There are other things here, but these two are the crucial for us in writing the code. Next thing, let's finally write that query, send it to API, and then download the raster file. All right, let's finally write that code and get the MODIS land cover data. So we will first of all call MODIStsp package, and then again from its function MODIStsp, so it's the same name. Now within this one, as we said, we don't need this general user interface, so we're just going to set it to false. For the out folder, we're going to be using main, which we already have defined beforehand. And then for the outs folder mods, we're also going to go for main. Here comes the part where we need to define the MODIS product that we want to use. And for that, we use cell prod arguments. Now, as I said at the very beginning when we went to a data set, it's very important that you know what is the actual name of that layer. So in our case, as we said, it's called land cover, and then underscore type, underscore yearly, underscore 500 meters. And then in the brackets next to this one, you need to set also that code. So the code is, if you copy that, MCD 12 Q1. So this is the full name of the product. Then you need to specify what is the actual layer that you want to download. And if you remember there, we chose the first layer, which was called LC1. So this is defined by band cell, which means band selection in short. So land cover 1 or LC1. Now that we have this, we need to define who is actually downloading here. And this is where you plug in, first of all, your username under user. Remember, it needs to be a string here. So I'm not putting anything here, it's empty. You need to fill out with your username. And also passwords. Again, it needs to be a string here. So please fill out with your own password that you registered and then confirmed. Then we're going to also opt for a temporal dimension, which is handled by start dates. And the last available year that I checked for this global land cover dataset is 2020. So we're going to do 1st of January 2020. This is how it's defined: 2020 dots 01, which is for the month, and then 01, this is for the actual day. We're going to do also definition of the end date. As we said, it needs to be 31st of December of that same year. So 2020 dot 12 dot 31. And now that we have defined this, we then need to tell to MODIStsp what is the actual format that we want to download. So we want to use that Ukraine file that we have. So spat math is going to be file. It's not going to be bbox. It's not going to be tile. And then we also need to specify what is the pathway to this file. Luckily for us, we've already created that. It's called file_path. And the final argument we'll be using here is the format of the product that we're going to download. And as we saw, we want to use gtiff or geotiff. Now that you have this, and you will also hopefully filled your user and password, you can simply run this, and then the download will start, as well as cropping of those styles. And what you should get in the end is a single file. So next thing, I will show you what I got, what is the name of it, and then we will move on to inspect this file and see what it has. If we run list files, what we will get is the files and folders in our main directory. And here you can notice several things. The first 4 files have names that relate to that dataset code that we just downloaded, but they don't seem to be TIFF files. Then we have a name, which it seems to be a name of the folder. It's the same name as for the shapefiles. Now, I actually inspected these files and folders, and what happens that object number 5, this Ukraine level 1, is actually a folder where our geotiff file is stored within another subfolder. So let's actually inspect this further. Let's actually set our path to be actually main plus that newly created folder, which is called Ukraine level 1. All right. And then let's inspect actually what this is. So it says here that we have 2 folders of files here. One is JSON MODIS file. So obviously refers again to this data that we were downloading, but the other one is folder. But this one actually has the name that we queried. So it's land cover type yearly 500 meters version 6. So let's actually add this one also to the fray. So let's actually write it here, and then let's enlist files within this folder now. Okay, so we get to the bottom of this. It says time series and LC1. Now, because we didn't really order any time series, and LC1 is the name of the layer that we wanted, I'm gonna also include here to this pathway LC1, and finally we can then inspect what is also here. And here it is. So here it is, the TIFF file that we just downloaded. So this is the TIFF file of global land cover for Ukraine. So what we will do next is we will use this pathway, and then we will load this raster file, and then we will finally inspect that raster file. So now that we have a pathway to our raster file, we also have the raster name. We can finally create a raster path, and then using this raster path, we pass it to Terra, and then using Terra, we load finally the raster file into R. So first of all, let's create a raster underscore path. And then here we can leverage the link to this last subfolder with one addition, and that is slash, which you actually distinguish between the last folder and the name of the file, which we already have, and it's this one. Okay, now we can run this and we just create a raster path. And now we can employ terra, its function rust, and just pass this raster path to it. And let's call our object Ukraine underscore LC, where LC is a shorthand for land cover. All right, now that we have done this, we can simply use terra rust and we'll load it. And then as we loaded this raster file, we can also inspect it. So here it is. So first of all, what we see here, so this is a spat raster. It's a typical class for Terra for raster files. Then we see also dimensions. This one has, these dimensions. So these are pixels. It has single layer, and then it has also other things here. So this is the extent that is using as well as the coordinates reference system. So this is because we did not really specify the coordinates reference system. Ideally, we will want to reproject this one to specifically, let's say, WGS84 and then use it thereon. So this is the plot of land cover for the bounding box of Ukraine. And on the right-hand side, you will see the legend with 17 values, and each represents a certain class. So what we would like to do is we would like to distinguish among these classes, and we would also like to see what is the prevalence of these different classes in every Ukrainian region. So this is what zonal statistics will help us do. One step before we do the zonal statistics would be to place this raster file and the polygon of Ukrainian regions into the same coordinate reference system so that we can actually then perform the zonal statistics. We will reproject the global land cover dataset for the Ukraine extent using the WGS84 coordinates reference system, and it turns out that our Ukraine polygon is already in WGS84, so we actually don't need to do any modifications about that. So the first thing we do is define this along-LATS WGS84 projection, and then we can actually reproject our Ukraine file. So if we go back to this place where we actually loaded, what we can do here is we can just simply take again this one, and then instead of just ending this loading of the file here, we can use a project function from Terra, which actually helps us reproject the current raster file. And for that, we will use the one that we defined, so CRS along LAT. And then we can simply just run this. And after we run this whole code, then we can actually check what is the coordinates reference system for Ukraine. I just quickly wanted to share with you how the raster file looks like after we projected it. It's more or less the same, but we can now finally see that the coordinates reference system is WGS84. You can also see that this change is reflected in the extent. The numbers are now different. So this actually allows us now to jump into zonal statistics and do the zonal statistics analysis, given that the raster file and that Ukraine polygon are now having the same coordinates reference system. Zonal statistics is a technique in spatial science, which is used to summarize or evaluate certain values over a certain region of interest. Most likely you will have certain raster values which come from satellite imagery, and then you would like to understand what are the sum of the values for specific spatial units for that raster. So for example, you would like to determine what is the average forest height for certain regions within a country. Or for example, what is, the pollution level for certain, cities. So what you need to have is some kind of a raster values, and then you need to have some polygons of interest. In our case, what we are interested in is to calculate what is the fractional cover area of a certain land cover class for a specific Ukrainian region. In other words, what we now have is the spatial presence of a certain class, let's say a forest or a cropland, grassland, and then we also have these polygons of Ukrainian regions. But we don't know is what is actually the share of different land cover classes for every Ukrainian region. And this is what zonal statistics will help us with. In this tutorial, we will touch upon several ways of doing zonal statistics when you have classes of land cover like we have. The first one will be a simple one, and we will be just determining what is the most dominant land cover per every region of Ukraine. The second one, we will single out a single class of a land cover, let's say croplands, and then we will see what is the share of croplands in every area of every region of Ukraine. So in other words, what is the fractional coverage of croplands for every region in Ukraine? And the third one, we will do this, but then apply for every land cover layer that exists out there. So we will start off by doing a basic zonal statistics that you can also apply in your use case, some other use cases. And this one is simply using the basic functions that are already defined in exact extract R. So let's first of all define a new object, which is going to be called Ukraine LC modes. Mode values are the values that are the most dominant for a certain area. So this is what we are going to use. Then we're going to call exact extract R and exact extract function, which is used for doing zonal statistics. And then here you need to provide two objects. The first one is the raster object with specific values. And in our case, this one has classes of land cover from 1 to 17. And the second object is a polygon over which you want to calculate these values. And finally, the third is the function that you want to apply. As we said, we're going to apply mode here, which is going to show us what is the most dominant land cover for every Ukrainian region. So this would be in short what we need to calculate. Now, we would also like this resulting object, which is going to be simply a list of values. We would like this to be joined with that spatial polygon of Ukrainian regions. But for that, we need to have some kind of a common fields so that we can join them. So let's then first actually create such a field, which is going to be called ID. And ID is going to be just a unique identifier for every Ukrainian region, and it's just going to be number from 1 to 27. So that means we need to go back to Ukraine poly, which is that polygon, and creates ID, which is going to be from 1 to the max number of rows of Ukraine poly objects. Okay, now that we have this, we can then take this ID column that we're going to create and append it to this object. And there is a very convenient function within exact extract. It's called append underscore calls. And over here, just specify that the name is ID. Simple as that. And then you also here can say that you don't want to track the progress, which we actually could. So if I omit this one, we're going to just track the progress of this process. And then the final step is simply to do an inner join between this object and our SF object, which is Ukraine poly. And we'll join them by ID. All right, this will give us a data frame, but we want to have simple features or SF object. So we need to add one more line to it, which is going to be SF, ST as SF. All right, and now when we run this whole thing, what we will get is the following. I'm going to show you actually now in a bit. So as you can see, first of all, there is this progress that was tracked. So we managed to do the zonal statistics. And now when we inspect this object, we can see that it has several things. Well, let me actually do it once more because it wasn't really applied. All right, this is better. So it's an SF object. It's WGS84, Coordinates Reference System of Ukraine. And here we actually see that it has 27 features. Each feature is a region, and each feature has an ID. And it has also the most dominant form of land cover, designating by the number. And for the first 10 values, we see it's mostly cropland. And we will, in the next step, actually create a ggplots map. And then you will see actually what is the most dominant form for every Ukrainian region. So let's do that. Well, first of all, we're going to create an object called map1. We're going to have 3 maps here in this tutorial. And then we're going to call ggplot function. And after we do that, because we are using SF object to create our layer, we need to call gmsf function. Within this one, our data is going to be this newly created Ukraine_LC_modes. And because this is our main aesthetics, we need to also specify AES arguments. And because within this layer, we want to fill the regional polygons, then our main argument is fill, and we're going to fill them with mode. But because mode is a number and we would like it to be categorical value, we just simply turn it into a factor here. So this is about the creation of the first one. Of course, we can specify here some of the constant values. For example, regional borders, we can, or boundaries, we can, let's say, turn them into white. And we can also determine the thickness of these regional boundaries with size, let's say, for example, 0.125 or something like that. Then we can leave it up to R to fill up the values the way it wants, so we don't need to deal with that. What we can specify, on the other hand, are how the legends is going to look like. So that's one of the things that we can do. So because we're using fill aesthetics, we need to specify guide legend for the fill in specific. So here we can, let's say, create a vertical legend. So our direction of the legend is going to be vertical. So that's the first thing. And there are several things that you can specify in guide. So I would like it to be in terms of squares. So I want it to be squares in vertical fashion. So then my key width, it's going to be in units, let's say 5 millimeters. And because I would like to create this square, then key height is also going to be units 5 millimeters. We can also specify tile position. Let's say it's going to be top. And we can also specify a label position of our legend keys, which is going to be right, the right-hand side, because I would like to put the legend on the left side. We can also specify the horizontal position of the labels and of the title. So for example, title.hJust will exactly do that. Let's put in the middle, so that's 0.5. And for example, also label.hJust, let's put them very, very close to the bar, so that would be 0, because 0 means left-hand side, 0.5 means mid-justified, and then 1 means right-hand side or right aligned. And then also what we can specify is the number of columns. That's going to be just one column since it's a vertical legend. And we can also specify that we don't want much of the space between rows, so by row equals false. Apart from the customization of the legend, we can also add some of the labels to our plot. One of them is, for example, a title. In this title, we can specify that we're looking at length cover for Ukraine. Then we can also specify something like caption. Within the caption, we can specify our data. We can say that this comes from MODIS, land, cover, type, annual, what was it? I think L3, global, and then 500 meters. And we can also, for example, if we don't want to have any graphicals, we can also omit that, both the X and Y axis. We're not going to have a subtitle, so that's fine. And then finally, we can also specify the theme. What I do like is to get rid of any excess backgrounds. So I use theme void, and then for specifics in terms of the font size and everything, I also specify theme. Now within theme, you can do different options. So one of them is, for example, we can specify the legend position, and let's say we're going to put it to the left-hand side. We can also specify, as I said, different labels here. So one of them is, for example, the plot title. And because we are here dealing with the text, we need to tell ggplot2 that it is the text. We can here determine the size. Let's say, for example, 22 is the size. We can also determine the color. Let's say, for example, it's going to be charcoal gray. There are some other things we can also justify, so my 0.5, and then we can also maybe put it a bit higher than usual. So let's say the vertical justification is going to be 1. So in a similar fashion, you can also specify some other things. Let's say, for example, plot caption. So for caption, we want caption to be smaller, let's say size 10. And we want it to be a bit lower than the map. So let's say we just -3. And we don't want it to be that pronounced. So let's say it's going to be a light gray color. And yeah, we can keep it horizontally justified. That's fine. We can also specify, for example, legend title, which is not a big of a deal, but we can also do that. Let's say we make it a bit smaller. We don't need to actually do any, I would say, horizontal or vertical justification, so that's totally fine. And then we can also specify, let's say, legend labels, also kind of enlarge them. Legend, yeah, labels. So, or legend text, actually, that's the right one. So for that one, we can do, let's say, a bit smaller size. We can also go for this color. Yeah, so these are the options. One other thing that we could also potentially do is, for example, increase the plot margins, because we will put that legend to the left-hand side. So maybe we should expand a bit the left side of the plot. So we can do that, as I said, we're using plot margin, and then within units, we specify several things. The top one, it's not going to change, so it's going to be 0, as well as the bottom one and the right hand side. But the left hand side, we can increase it. So if you want to increase, add a bit more space, then you add a positive value, let's say 5. And then within this one, we just need to specify our units, let's say lines. And yeah, that would be it. This is how you define it. So then we can just simply, run this whole code. And once we run that, we can then just simply print this first map so that you can see what we got. And after, if we are happy, of course, with the outcome, then we can move on to the second type of zonal statistics, which is going to be a bit more complicated, so stay tuned. All right, so this is our first map. It's the land cover for Ukraine, which shows the most dominant land cover per region. And because we organized it by category, it shows us specific color for every category. One thing that you can see that is the value of 12, which dominates the landscape, and 12 in the codebook, that is the cropland. So that's quite interesting. And because cropland is by far the most dominant land cover in Ukraine, then in the next step, we'll actually analyze what is the actual fractional cover of every region for cropland. In other words, what is the area that cropland occupies in every region? One of the very cool features about exact extract R is that you can use some of the existing functions to calculate the values for your area of interest, but you can also customize those functions. So in our case, we have classes, we have 17 classes of land cover. So we cannot simply average them or count or anything like that. We need a function that would calculate the size of the area under a certain, let's say, land cover class. And we can precisely use exact extract for that. It's pretty straightforward. I will show you how. But in the first step, what we will do is we will first remind ourselves what are those actually classes, one of the 17 classes that exist. And as you can see, one of those classes is croplands. So that's number 12. So I will first show you how you can analyze a single class using zonal statistics. In other words, what I want to get from this zonal statistics is what is the area under croplands for every Ukrainian region. So let's do that. Let's write our codes, and we're going to call this first object Ukraine croplands. And then we're going to use exact extract R and its exact extract function. And then within this function, as we said previously, you first need to define what is the raster from which you're taking values, from which you will calculate the value. So in our case, that's called Ukraine LC, which is a shorthand for land cover rights. And then the second one needs to be the polygon for which you are calculating these values. So for us, that's Ukraine poly. We are able to analyze this because we have them in the same coordinates reference system, so there won't be any problems there. Now comes the fun part. And this is where we actually have to define a function. So usually if you don't need to define a function, you simply write here, let's say mean, or you write minimum or maximum or something like that. But in our case, because we have classes, we cannot really use those, standard functions. So we need to create a function that will allow us to actually perform, this analysis. Now, there is a very generic thing here about exact extract, which is you can actually specify here certain generic parameters. And then based on those parameters, this function will calculate them based on these two data points that you provided. So the raster file and the polygon. So what we want to do here is we want to calculate the percentage of the area covered by a certain value. In this case, the value is 12, which is the value for the cropland. So we want to calculate what is the area that cropland occupies for every Ukrainian region. So what we need to do is we need to sum the fraction of values that are 12 by the sum of all the fractions. So for the whole basically region. So here in this function, we specify two generic parameters. The first one is value. Basically, what is the value for which you want to do this? And the second one is fraction, which is actually simply an argument for calculating the fraction for every region. And then within this curly brackets comes the actual formula. So the formula is the following. It's going to be the sum of the fraction where value of our class within the raster equals 12, which is for the cropland, and then divided by the sum of fraction. So in other words, what we're looking at here is the ratio between the fraction of the cropland divided by the area size of that specific region, for every specific region. So what we will get in the end is only for croplands, what is the area under croplands? And because we want to have percentages, we can just add here 100 times and then this formula. So once you run this, you will next get actually those values. So once we inspect this newly created Ukraine cropland object, we find out it's actually a list of 27 values, where each value represents the fractional cover area for cropland for every Ukrainian region. So this is exactly what we wanted, but it's still not in a user-friendly format because it's a list. What we would ideally like to have is a data frame. And instead of being like organized in this kind of a very wide format, we would like to have it in a long format. So the first thing is to create this data frame, which is actually going to be based on this list. The way to do that is using the asDataFrame base R function. And then we also want to transpose these, this list. So we want to have a column name for each of these lists, where a column name would be actually that specific region. So we just pass the Ukrainian cropland here, and then we also run this. And as we run, I just want to show you how this actually now looks like. So it's now a data frame, and it has actually 27 columns, and every column has only one row, where each row represents now this fractional cover area. What we would like to do, as previously I've said, is instead of having these, we would like to pivot this to a longer table. So now we currently have a wide format, but neither ggplot2 or any other data visualization tools within R, they do not really fare well with wide formats. So we need a long format in a way that one column will be, this region identifier, and the other column will be simply this fractional cover value. Luckily for us, we have a solution for that. So we can then just name this one differently. Let's call it long. But we will be working with this newly created Ukraine cropland DF. And then within this one, what we can do, make a pipeline, and then we apply tidier package from tidyverse, and especially its function pivot longer, which is gonna help us transform this wide into a long format. Now, what you need to do next is the following. So yes, we did specify this name. Next thing we need to specify, okay, how many columns are we really talking about? So we have 27 columns, so we need to specify cols equals from 1 to 27. So we're not going to capture all of them. And then you need to give the name to this first column. So those values V1 to V27. Let's call this, so it's names2. So let's call this one simply ID. And then the second parameter, or a third actually in this case, you need to specify is values2. In other words, how are we going to call this a values column? So we can just call it value. It's also fine. Yeah, so this is how you transform any kind of a data frame from a wide to a long format. Now let's run quickly this. And after we ran, I want to show you now how this looks like. Here it is. So it's transformed into data frame. Now it has two columns. One is ID column, where every value is the value, like unique ID for Ukraine region. And the other value is actually fractional cover area for cropland. So one very cool thing about the way exact extractor works is it actually organizes, it orders these based on the order from the polygon that we have. So we actually don't need a join key in this case. What we just need in the next step is simply merge this the way it is, merge it with the existing polygons. So let's just quickly merge the two and create a new object, which is going to be called Ukraine cropland SF. For column-wise merging, we just need to use cbind from base R and then specify, first of all, the Ukraine polygon, and second, the cropland df long, which you just created. And then we can just run this. And once we run this, we can then inspect the newly created object. So this is the newly created object. So it's a simple features object. It has, of course, 27 features, and it has 8 fields. And one of them is this value field that we just created, which shows actually what is the fractional coverage area of cropland for every Ukrainian region. We're almost ready to create our second map, but this time I would like to include a bit more information. So since we now have a single class and we have the percentage of fractional cover for every region, I would also like to include the name of the region and also that fractional cover percentage for every region. So I would like to annotate the map and put it in the middle. For that, we will need to create the centroids based on that Ukraine cropland SF simple features object that we have. This is how we're going to do it. So region centroids. And now, so we're going to create an object called Ukraine region sense. And this one, as I said, is going to be based on the last one that we created, Ukraine cropland SF. And then we're going to build a pipe and we will build centroids. It's really straightforward using SF package. You just need to use st centroids and it's going to do it for you. And once we do that, we can actually specify what are the longitude and latitudes columns here, because we want eventually to turn this one into data frame so that we can create annotations in ggplot2. So for that, we need to use dplyr and mutate option, which is then used to create longitude fields. So because longitude and latitude fields are created from the geometry field that exists in simple feature object, and because geometry field is a list, we need to unlist that list and then take the first element for the longitude and the second element for the latitude. So we then use unlist and then we map the geometry fields and the first one from it. So we use the same for the latitude with one difference, and that being we use the second here, second element. So this is also lat. All right, then we continue with our pipe, and this time I want to select only those features that I need for the data frame. So one of them is the name of the region, and in our case it's called shape name. Then I want to grab both longitude and latitude measures. And finally, I would like to take the value so that I can then print both the value and the region. And then the last step is to get rid of that geometry field. So we can use from SF package st drop geometry. So now that we can run this, and once we run this, we can also inspect these objects. So this object is a data frame, as you can see here. And as you can see, it has 27 fields and it has the region names. It has longitude, latitude measures in WGS84, which corresponds with the coordinates reference system for our shapefile. And then finally, it has values. These are the percentage cover fractions coverage for the croplands. So this is how much croplands there are. All right, we can now start creating the second map, and we can do that by first of all using the code for the first map as our baseline. So we're just going to rename this to map 2, and we're going to rename also this to map 2. So this is going to be our main code. Now here we're going to use this newly created shapefile. So we're still using geom.sf. And here, instead of creating categorical filling aesthetics, we're going to use values which are continuous, which is going to also down the line affect what we also define here. Now here, we would like to annotate this map. So there are two options here. One of them is geom text, which is the integral part of ggplot2. Another one is to use ggRepel package. This time I opt for the geom text because I don't expect those annotations to be really crowded because there are only 27 regions, so more or less should be fine. Now within geom text, first of all, we define the data source. In our case, it's Ukraine region cents. Because this annotation is another layer, we need to specify aesthetics. And then within aesthetics, we need to specify the longitude as X, latitude as Y values for those coordinates, and then the label. Now, for the label, I would like to show two things. One is the name of the region, and the second one is the percentage of this fractional cover area. And I would like that to be in the same line. So because we are here gluing together several pieces, we need to use paste. And paste null would be actually a good option. Second thing is for the region name, we can use shape name. Then we would like, for example, to put colon there. So we also add that. As you can see, we define that as a string. That's the most important part because text is a string, right? And then I would like to have some empty space, and this is how you add it. You also notice that I put comma after each element. So this is necessary if you don't want to ggplot to throw an error. And then I would like to print value. But if you remember from the previous screen, values have a lot of decimal places. So I would like to round values to, let's say, no decimal places. So that would be 0. And then finally, at the very end, I would like to add here a percentage also symbol that will stand next to the value. So that's one of the things. Now, previously, we did not really define colors because we just operated with the categorical values and I let R create the color values for us. This time, we're operating with a continuous measure, so the scale is going to be continuous. And if I let R fill this up with the default color values, it's going to be blue color scale, which doesn't make much sense because we're looking at crop lengths. Instead, I suggest that we define the colors on our own and that we use terrain colors, which are quite nice. They also have both orange and green, which I would say squares well with crop lengths. So because we are using fill aesthetics, it needs to be scale fill. But because we're using a continuous scale, it cannot be scale fill manual. It can be, let's say, scale fill continuous, or in our case, because I want to use gradient color, gradient. Now within this one, we need to specify several things. One of them, which is optional, is the title of the legends. I would like to make sure that people know what's going on. So it's fractional percentage of fractional cover area. We can also specify, as I said, colors. And as I said, we're going to use terrain colors, which are part of this function. Let's say 6 values. And also I'm going to reverse them because otherwise a null value is going to be colorful and then last value is going to be, white or almost white. So I just want to reverse them. And I can also set the limits because we are dealing here with percentages. I can say comfortably from 0 to 100. So that's another thing. Now moving on to the legends, because we're dealing here with the continuous scale, I would like to make legend horizontal. It really reminds me of continuous scale. In contrast, for example, we previously used the vertical one for the categorical, which more reminds me of, the categorical scale. So we change here the position. It's going to be horizontal. And then I would like this key heights, which is thickness. I would like it to be a bit smaller. So let's say 2.5. And I would it to be a bit longer, let's say 10. Label position now comes underneath the legend, so it's going to be at the bottom. And then I would also like this to be justified. The number of rows now is 1. And we also want them to be next to each other. So there is that. All right, after the legends, what we can also specify here, we can change a bit. So we can say croplands Ukraine. We can keep the caption as well as these other things. Legend position, perhaps it would be a nice thing to put it on the top. In terms of the title, there is not much to change here. Perhaps, well, one is going to push the title a bit to the upper part of the plot, which is good for us because then we can fit in the legend. Caption is fine as well as the legend title and legend text. There's not much about that. One thing that we can change here is the plot margins. We don't really need any more space on this side. Maybe we can add some more space to the top part, but it's not really necessary. I think it's going to be fine. All right, now that we have this, we just once more check if we actually connected all the parts of the ggplot2 with pluses. Seems we did. So we can now just run this and then inspect the map, the annotated map of croplands cover fraction area that we have. And here it is, the croplands map of Ukraine showing the fractional cover area for every region. So we can clearly now see what are the regions that have more or less croplands, and this gives us actually a better picture. So yes, in some regions, indeed, croplands are dominant, but they're not by far, they don't have such a big share. There are regions where there's more share, and there's regions where there's less share of croplands. You also see that we annotated the map. There is perhaps a bit of overlap in this Khmelnytsky and Ternopil oblasts. But otherwise, looks pretty much fine. If you want, you can also try the thing with ggRepel, and perhaps it's going to be a bit better. Also, I'm pretty fine with the colors and the scale, and I like how it goes from 0, which is like whitish, to 100, which is green, and then transitions from orange to yellow and then to green. So looks pretty awesome. And now we can get to the third and the final stage of our zonal statistics analysis, where I'm going to show you how you can actually do zonal statistics when you have multiple classes of land cover. All right, we are ready for the third and the final stage of zonal statistics, where I will show you how you can calculate land cover, fractional coverage area for every land cover class and for every Ukrainian region. Let's get started. The first thing is that we need to define the number of classes. What we know is that there are 17 classes, and we also know that there are represented as numeric numbers in our raster file. So we can actually go and use terra once more and define the minimum and maximum values of terra. And then we can take those minimum and maximum values and then just create a range from 2. This is how we're going to do it. First of all, we're going to create an object called LC values. And then we're going to use terra. And terra has a very nice function, which is called min-max, which can return, as I said, minimum and maximum values from a raster file. In our case, that's Ukraine underscore LC. And once we do that, we can then create classes. So here we can do, so because this is going to create an array of basically minimum and maximum values, so only 2 values. The first one is going to be the minimum. So we can take the first element from LC values, which is going to be minimum, and then we take also the second one, and then we create simply the range between the minimum and maximum values that we just grabbed from this Ukrainian LC. All right, so that's the first step. Now, the second step is the actual zonal statistics that we're going to perform. And the thing about the zonal statistics here is that, first of all, we can define a general zonal statistic. So basically this way, zonal stats Ukraine, for example, and then using exact extract R, and then its function exact extract. So we're just going to first do those general zonal statistics, and then we're going to create a table of proportions in the form of a list for every land cover class and then for every region, where every member of the list is going to be one region. So 1 to 27. So for now, we just create this object, which is generally a zonal statistics, and then we will pass it to a more customized function, just as we did in the step before. But this time we will create zonal statistics for every single land cover class. So this is the first step. All right. So in the next step, we finally can do the Ukraine underscore multiclass. So here, the thing is the following. Because we have 27 regions and we want for every region to calculate the fractional coverage area for every of the 17 classes of land cover, that means that we need to use lapply. So basically we're going to apply function to a list, because otherwise we wouldn't be able to perform this, because here we actually have 3 dimensions. We have land cover classes, we have Ukrainian regions, and then we have the fractional cover values themselves. In the previous step, we didn't have this. We had only two dimensions, so we didn't really need to pass the list. Now we need to create a list where every member of the list, as I said, is one Ukrainian region, and then within every list, we will have 17 values. So for each of the land cover classes, we will have its percentage coverage of that area. So we can draw here on this object that we already did. So a general zonal statistics for for the Ukrainian regions. And then here, as we did in the previous step, we can create a function. But here we're just going to call it x. And then we did this one, we can then do things. So the first thing is we're going to create a data frame within this list. Now, we're going to use a function from base R, which is going to create marginal effects tables. In other words, it's going to create proportions for each of the members of the list. This one is called prop.table. And now within this one, we're going to say the following. Create a table where we have a factor. Why do we use factor? Well, because the classes themselves are unique, right? So we don't want to have a continuous values. So the factor of x, which is our defined function object, and then for every row, starting from 1. So we then define levels which are going to correspond to the classes. As simple as this. So then what do we have here? We have zonal statistic results. We have them putting into data frame, which is going to be prop table, so proportions table. And then within this one, we course it to table, which is going to show us, so basically for every class is going to show us percentage coverage values of every land cover class. That's how it is. All right. We just need to now check if we actually closed all the brackets possible, because here there are plenty of them. So this is the first one, this is the second, then this one is also here, which is closed. I think we missed one. We missed one here. Or actually, no, this one is fine. This one is an extra one. So now we have everything. All right. Now we can actually, well, we cannot really run, but we can run in the sense that you can see what we actually got here. Well, let's run actually one by one. All right. Let's first of all run this one that creates min and max values so you can see what actually is going on under the hood. So this is what we get here. So this is the first output. So these are the minimum and max values, as we said, from 1 to 17. Then in the next step, we created object classes, which is a range of values from 1 to 17. Why do we do this? Well, we do this because we want to create marginal tables of marginal values for every land cover class for every Ukrainian region. And as you can see, classes are indeed 1 to 17. They are put into a list. So we have also that. Then we just ran this zonal statistics. The output of this one, it's not really needed. I mean, it's not something that I would need to show here because it's simply going to create, you know, those 27 values land cover. But more importantly is this one here, because this one is the place where we actually applied a function to the list where we created these proportion tables. So we can finally run this and we will create Ukraine multiclass object. Now, I would like just to show you, because it's a list, we can simply, print it here. And what we should get here is the following. We should get a list of 27 members, right? So here it is, as you can see. So this is number 27. As you can see, it has 17 columns where rows where each row represents one land cover class. And then the next one is frequency, which shows the percentage of the area that is covered by, any of these. Now, the thing is, of course, if you want to work with ggplot now, you cannot really work with this format. So what you essentially need here is we need to create a data frame out of these lists, right? So we need to actually create we need to bind rows. And luckily for us, dplyr from tidyverse has exactly that function. So bind rows, which we are going to use now to create that. So here's how we are going to do it. We're going to create a new object, Ukraine multiclass underscore df to show that we're actually going to convert into a data frame. And then we use dplyr. And as I said, there's a very convenient function, bind rows. What this function is going to do for us, it's going to coerce that list into a data frame, but it's also going to help us create a separate column, which will then capture actually regions. So essentially we will have 3 columns. One is going to be a region ID, a second one is going to be a land cover ID, and the third one is going to be the fractional cover values. So in other words, we are going to convert our, let's say, list object into data frame, and it's going to be in the long format. And this is how we do it. It's basically just, 2 lines of code. So we use the previously created Ukraine multiclass, and then here we specify the ID field. ID here meaning the ID of the list, so each member of the list, and we say that we want to name it ID. That's all. All right, and then we can run this, and after we run this, we can also inspect. So let me just now increase this a bit. So we can inspect Ukraine multiclass df like this, and it has 459 values. And as you can see, or actually, hold on, you can see now ID. So this is the ID of the region. var1 is the actual land cover class, and then frequency is that fractional coverage area in percentages. Now, before we move further, we can just change those names for this newly created object and assign them something actually else. So what we can do is, for example, keep ID as is to signify the region ID. And then for that var1, let's specify that we're talking about the LC class ID. And finally, the last one can be simply the value as is. All right, so that's one thing. Now, Currently, we do have a problem here because this LC class ID is simply a number. We don't really know what it signifies. And we do have that codebook with the strings, but it's on that website. And if we want to actually create this, yeah, one of the options would be to do it manually, but it's going to take a lot of time. I actually suggest that we scrape that page, get those values we need, put them into data frame, and then actually assign those values to our raster. In a way, let's assign them actually to a specific data frame and then merge them actually with a raster, and then we merge them also with the SF file. And then we can actually plot that in ggplot2. So if you're wondering how we can do that, here is how we can do it. So let's actually name this section that we're going to work on. So scrape land cover codebook. And then here we are going to use HTTR, and we're going to use its get function in order to get a response from the website. And the website is, so if we go back to that website before, so this would be the website link. So yeah, it's a bit longer. So then once we do that, we want to grab the contents. So let's call that content txt or just text. And then again, we use HTTR and its function content, where we actually employ this link res that we just created, this post, and we say that we want a text from this one. All right, and then the final step in this process of scraping is to turn this actual text, HTML text, into a data frame. And once we do that, I'm going to show you how this data frame looks like and what we're going to do about it. So let's call this data frame simply df. And for that, we use a read CSV function. And just for the text, we say it's the object txt. It's as easy as this. All right. Now we can run this whole thing that we just did. And once we run this, let's inspect this df so that I can show you what we actually scraped and turned into a data frame. So you might be scared with the looks of this data frame, but essentially this is everything that we pulled from that HTML file. We pulled here into this data frame, and we simply created a single column where every row basically is every row from that HTML file. So now what you can see here is basically everything there. So perhaps you might want to, go back and see, what's going on here so that you can figure out what's going on actually. But once you get to this row 281, you do notice the glimpse of a codebook. So it's here. Here it is. Now the only question is, where is the part where we have description of every class? So if you go a bit down further, here you can find it actually, finally. So it starts somewhere from the row 449. So this is the one where it starts with water. And then it actually has here, for every of the 17 classes. So ends somewhere with a row, let's say 474 or 475, where barren or sparsely vegetated land cover is the last one. So what we need to do next is just take those rows from this table that we need, and after that we will do some cutting, and finally what we essentially want from this whole data frame is simply we just want, for every row, we just wanted this single value which shows us what is the land cover. So let's get down to business and do that. So as we said, what we essentially want, let's create a new object, let's say D. And as we said, we want to filter rows. So we're going to take from 449 to 475. And then we want, once we get this, we want again to declare it as data frame. Because if you take only rows like this from a single column, it's going to most likely end up in a list, but we still want to keep it like this. And then once we get the data frame, it's still gonna be just a single column. And I would suggest that we here change the name to simply calls, or it can be just call, whatever, to signify something at least, that we know what we're doing. And then once we do this, I think we don't really need to go back to see what's going on, because we already know that it's just going to take those rows, specific rows, to the codebook, and it's going to create a single column. Now, what we need to do is we need to split this. Why? We need to split because we want to keep only those rows where you have that value signifying the land cover class, and we want to discard everything else. So here's my thinking. So I'm thinking to take this and then use that, unit 5 or unit 8 that exists right after every land cover class label, and use that actually as a separator. So let me actually show you. I will need actually to then run this quickly, and then also show you what I mean by this. Let's, for example, print this D, so that you have a better idea what actually I'm talking about here. So let's just print this D. So here is in a nutshell what's going on. You see here water, and then after water you have this uint8. You also have this situation, woody savannas, for example, and then you have a space and then unit 8. So essentially what I'm suggesting is whenever you have this uint8 or you have unit 8, basically creates two columns separated by this or this unit 8. And then after that, just after we create these two columns, just remove the one that we don't need. As simply as that. So we can actually now move on to that part. So we can work with this object D, and we can create a new, let's say, object, which is going to be called class SDF, where we're going to do all this shenanigans. So we write a pipe starting from D, and then we again call to rescue tidier, which has a really nice function called separate, which will allow us to separate these calls that we just created into two, as I said. The left one is something we're going to keep, and I'm going to call it keep, and the right one is something we're going to discard, so I'm just going to call discard. Now we need to specify how we're going to separate this into two columns. What is going to be the separator? So sep as a shorthand for separator, and then here we can use some of the regular expression to do that. And this is how you can actually define two essentially separators, because remember we have that unit 8 and then we have some kind of a uint8, but we need to use both of them as separators. So you do like this using regular expression or regex. So slash slash and then s, and then you open the brackets where you actually specify what are those separators are going to be, and each separator is going to be separated by just like a horizontal line like this, question mark and then equals to, and then after that you specify what these are. So the first one is called unit 8 and then separated by this vertical line, and then the other one is uint8. And once we do that, we can create the final pipe here where we simply select only this keep column. Okay, let's try this out, right? Let's try this out. So first of all, let's run this, and after we run, we can then inspect this class SDF. So this is what I was talking about. As you can see, we now have a single column. It's called keep. And then within this keep, we only have the names of the land cover classes. This is exactly what we wanted to do. This is exactly what we want to achieve. So as you can see, we do have, however, here, a bit more rows than we anticipated. So we anticipated 17, but you can see here we have actually 27. And the reason for that you can find in rows, let's say 14, 19, 22. Basically here are the parts that got empty after we did the split. So what we actually need to do next is just discard those rows where so just discard those rows where you actually that are empty. We simply don't need them. And this is going to be very, very easy to do. So the way you can do that is the following. First of all, we're going to create an object called unique classes, where we're going to store unique values from that keep column. So unique, and then classes df keep. Okay. So now we're going to actually decrease from those 27, we're going to decrease to 18. Why? Because unique values are going to be 17 actually string values and one which is empty. So we already kind of narrowed down that. But in order to remove the empty rows, we again need to use a regular expression. And this is how we're going to define. We're going to say, we're going to define empty lines, and we're going to use grapple to grab those instances, those rows. So as I said, we use a regular expression, and we use the regular expression like this. So hats and then slash slash s, and then for every instance that is empty, exemplified like this, we're going to apply this regular expression to unique classes that we have defined. All right. And then in the final stage, we're going to subset these unique classes and get rid of the empty lines. So let's create an LC classes list. And then from the unique classes, we use this exclamation mark, which is in R used to exclude. So we exclude empty underscore lines. Now we can run actually this whole thing, starting from here. And then I'm actually going to show you what this list actually means. So what we actually got here. So this is it. We have 17 values now. These are the 17 classes. So we finally managed to, to grab them. So we finally have them. And this is how you can do the scraping from that website. But actually, if you're using MODIS, you can basically scrap anything using this method. I think the only thing you need to change here is those rows that you want to grab eventually. So, and then discard everything else. But everything from there on, every single function, it's pretty much straightforward, and you can just like use that for that purpose. Now that we have this, what we want to do next is we want to create a small data frame based on this, where we will have just those classes as one column, and we will have IDs as a second column. Why are we doing this? We're doing this because if you remember the previously created data frame with multi-classes zonal statistics, it has also that ID field. So we're gonna now create that field so that we can just merge them. And the data frame is gonna be called LC classes df. And we need to use data frame argument from base R here to do that. So we're gonna create two columns. One is gonna be LC class ID. So this is something that we also have in that previous one. Now we're going to actually turn it into a factor because in our original file, Ukraine multiclass df, it's also factored. And now we can define the levels of this factor, and which is going to be 1, 2, and the maximum we would put here 17. But then again, if we go back to that codebook online, we will see that the valid values are from 0 to 16. And here we have from 1 to 17. Now we don't have 0 here, which obviously is going to be water. But then 17 is not really included also in the codebook. So I actually checked, And it turns out that 17 corresponds to water, actually permanent water bodies like sea or lake. So what we actually need to do here, we need to specify 1 to 16. Now, I can specify 1 to 16, it's not a big deal. But what if you're working with a different data set from MODIS and you have a different number of classes? I want to here tailor this solution so that when you're running this code, you actually can also use what you need. Now, it's going to be a bit difficult in this case because we need to get rid of one of the classes because, MODIS screwed it up this time. But what we can do here is we can take the length of this LC classes list. Now, if you specify like this, it is going to define values from 1 to 17. But because we want from 1 to 16, we just add here -1. And this is going to give us a factor with levels from 1 to 16. And then the last one we want to specify in this data frame is the class column, which is going to grab those string classes. But now again, we here have 17. And because number 17 we don't really have, and actually we have numbers 17, but the thing is that number 17, so it's snow, actually the last one, barren lands, actually it's a 0 that does not correspond, so water. So we need to get rid of the first one. And the way you get rid is you simply put -1 here. So once we run this and then we inspect this file, what we get here is values from 1 to 16. And as you can see, it doesn't start with water. We had to get rid of the water. And it ends with 16, which is barren or sparsely vegetated. Now that we have this object, we can then finally join this with the zonal statistics results. And then we can finally, for the zonal statistics object, now get also the labels for every land cover. And in the last step, we can join this object of zonal statistic results with labels of land covers with the polygons of Ukrainian regions. And then in the final step, we can use that object to create a map in ggplot2. Now that we have those land cover names, what we can do is we can merge them together with the land cover fractional coverage percentages. And then we can actually have together zonal statistics and the names for each class. But it doesn't end there, because in the last step, we then want to merge this one with the actual polygons of Ukrainian regions so that we can finally do the mapping in ggplot2. So in the first step, let us create an object based on this one, Ukraine multiclass df, where we stole those zonal statistics, if you remember, for every land cover class and for every Ukrainian region. And let's just call them labs, because we're gonna add labels to this one. Then we're gonna create a pipe and use left join from dplyr and add here the object that we just created. So it's this one, lc classes df, and use as our join field lc class underscore. Okay, so this is the first step. So let me actually quickly show you what this is gonna do by just running this code. And then we can also print this so that you can also get a better sense of what is actually that we created. So we created 459 rows still, so everything is fine. Nothing was dropped from that original zonal statistics data frame. Now, this cannot fit this new column, but what we essentially have here, so we have ID of the region, we have ID of the land cover class, we have fractional coverage value, and then as the fourth and the new addition for that newly created data frame, now we have for every land cover class also its name. So that's great. Now we can move to the final stage, which involves joining this object with that Ukraine poly object. This is basically the object where we have which is a shapefile of Ukrainian regions. So let's create the final object, which is going to be called Ukrainian multiclass SF, to, in other words, say that we are now working with simple features. And then let's create a pipe from this Ukraine poly. And let's make sure, actually, that the join fields is of the same class. Now, the join field here, it cannot be the same as it was here, because in the Ukraine poly, we only have regional IDs. So that's going to be the only field. Luckily for us, we also have region IDs in this one, so we can use ID. So let's first of all make sure they're of the same kind, which they are currently not, because the ID in this Ukraine poly is actually categorical, factor variable. And in this one, it's a character. So let's coerce it to character in this Ukraine poly so that we can then join. So this is done through mutate. And we just, actually, we're not going to create a new one. We're just going to update this ID and just say as character ID. As simple as that. And then we create another pipe. And finally, we can do left join using the plier. And we left join this object. So Ukraine multiclass df left that we previously created, and then the join field is going to be ID. Now we can run this chunk, and as a final step also explore this. So what you see here is, so for the Kherson region, we can see the first 10 values. So what we can see here is for land cover classes from 1 to 10, which are here from water to savannas, these are the values that we have. So these are the ratios that we have. They're not percentages because we need to multiply by 100, which you can do in a bit. So now we actually have exactly what we need. So in the next step, we can finally go to ggplot2, and then we can create a map that will help us actually see what is the percentage coverage area, fractional coverage area for every land cover class and for every region. The time is ripe to create the final map where we will be presenting actually a plot with multiple maps, where each map is going to show you for every class what is the fractional coverage percentage per Ukrainian region. So instead of writing the code from the scratch, we can simply use the code from the second map, because also there we used fractional coverage percentage, but only for a single class, which was cropland. So here we can rename this one to map 3. And then we can also take a different data source, which in our case is going to be the last object we created, Ukraine multiclass SF. Now you do remember that in this one we have that class 17, but we don't really actually use it. That would be, NA. So what we can do here is we can simply subset this data frame, and we can say here that for those class IDs where we have 17, that we just discard them. So that would be then LC class ID does not equal 17. So this would be then filtered out. We're still using values here, but if you remember, the values in the current data sets are not turned into percentages, they're still ratios. So we simply need to multiply them 100 to get the percentages. Now, in terms of the text here, I would not use the text because anyways, we're going to have, 17 maps, so it's not going to really be visible. So I'm just going to keep this, commented out. If you would like to try out and maybe annotate, let's say, Ukrainian regions and or these fractional coverage values, you can also try it out. In order to create, subplots, we just need one line of code, and this one called faceted rep function from R. Basically here, you just need to specify what is the column from your data that you want to use to create these facets or subplots within a plot. In our case, we're going to use class, which is the string value for every land cover class. And then we're just going to add here plus, and then move on. In terms of the color values, I would still keep the terrain colors and file values, as well as the limits and the legend title. Also, I would not really touch the guides, so I'm happy with the legend as well as the labels. Same applies to the theme. The only thing I would change here is the plot margin. I think I'm just gonna remove this left-hand side extra space. And finally, rename this one to map3 so that we can run this chunk and then also print it. All right, ladies and gents, here it is, the final plot where we combined 16 maps into a single map, where each actually map or subplot here shows you what is the percentage of fractional cover area for every land cover class per Ukrainian region. And one of the things that you can notice right off the bat is we have a single legend here, which is so neat and helps us just focus on each of these maps and see, what is, the coverage area of each of the land cover classes. Another thing that stands out is definitely the croplands. So most actually of the regions have croplands as the cover that dominates the landscape. There are some other types, most dominantly forests as well as grassland. It is also there, but croplands are by far the most dominant here, as you can see in the first line, the fourth map. So this map, of course, can be improved. There are some things like, for example, the titles, perhaps they could be made greater, or maybe you could put even some frames around this map to kind of distinguish among them. And of course, there is always the question of color, whether you want to change that. But yeah, this is more or less, this is it. This is how you create different maps based on zonal statistics analysis. And this is how in specific you do it for the lands cover dataset from MODIS. All right, that's all for today, people. In today's tutorial, you hopefully learned how to do zonal statistics when you have raster files with one or more classes. In today's tutorial, we access a MODIS satellite data on global land cover using a dedicated R package, which serves as a client to communicate with the MODIS API. We also created several maps of global land cover, fractional cover area for every Ukrainian region. So this one opens up a broad space for you to do for any other country around the world, any other country of your choice, or even a region. So if you would like to replicate this analysis, you can check the link below in the description. So feel free to clone, reuse, modify this repo as you find fit. But I'm really looking forward to seeing what you make out of this tutorial and where you take it on a travel across the world. If you have any questions, comments, or general feedback, feel free to reach out to me here on YouTube, but also on Instagram and Twitter. If you're new to R, or you are not new to R, but you would like to expand your knowledge of GIS and data visualization with R, I prepared a few tutorials for you. See you next time.